So now I'm hoping people can hear me. Let me just finish up here. I need to go get the chat and pop the chat window out so that everybody can see it. Pop out. Okay, we're almost ready to go here. Again, apologies for the sort of challenging start here to get us going. I'm trying to, oh, that's not the right window. Hold on. So I'm headed over to this one, maybe? No? That one? It's not letting me grab it. Let me hide this for a second. Tuck this away. So one more try here. Just trying to get the chat working. If you're watching this on the video, you might want to skip ahead like 2 or 3 minutes just to skip over all of the silliness. All right, so open this up. So what I want to know is how did the pros do this? People who stream on Twitch. Well, I suppose they never stop streaming. That's the real key. And if you're doing this 18 hours a day, you've probably got a pretty good system set up. Come on. All right, one more try. Pop out the window. Hide that one away. And then, okay, that seems a little better. And then we just need to move this over here. Make it a reasonable size so everybody can see it. All right, I think we're in better shape now. Let me move this out of the way. And I think we're going to be good to go. The last thing I need that I really should have is my iPad stylus. Let me go and grab that. It's in the other room. And I'll be right back and we'll get going. All right, we are in business. So again, this is a streaming session where we're going to look at some more abstract algebra concepts. We've got a quiz coming up tomorrow. That quiz is going to cover using Cayley tables to organize information about a group, and then also implementing those Cayley tables to do computations with the elements of that group. And then thing 2 is also using and understanding the formative properties that make a group a group. So first of all, the definition, associativity, identity, inverses, and closure. And then also some of the basic properties that those things imply. So I'm thinking here of the uniqueness of identity, the uniqueness of inverses, the left and right cancellation properties, and the shoes and socks formula for the inverse of a product. So what I want to do today is just go through a few examples. Ideally, Ideally, examples drawn from the ones that you'd like to talk about. So if you have questions or particular problems that you're getting stuck on the homework, please do throw them into the Twitch stream chat. Or if you're not logged into your Twitch account, feel free to throw them into the place I've set up for you in our Slack channel, so that as we're going through today, I can try to be responsive to your questions. If you don't have any questions of your own, then of course I'm happy to just pull a few sort of out of the old memory bank and try and go through a few together that I select. But I'd much rather you pick the problems than I pick the problems. So let me take a moment and just get a copy of our textbook up on my other screen here so that we can borrow some problems from it as we need to. Again, you can find this online book at the web address that's right here on the screen, mathematics.com/abstract. Just don't forget to double that T for mathematics in my website address. We are looking this week at the exercises that show up under chapters 1 and 2. So I'm going to jump into chapter 2's exercises here and try and find an exercise or two to just get us sort of kick-started along the way here. So let's, whoops, sorry about that. I might as well drag this over for a minute. Let me collapse the table of contents. And let's go find an example of something to work on. So here's a problem that I like. And I don't want to do the whole problem because there's a lot of steps to it. But I was working with a student in office hours the other day on this problem, and I thought it was really neat. It was a good way for us to sort of get oriented to how the properties, the founding properties of a group actually work. And it's this problem right here, problem number 7. So let me grab a snapshot of it so that we can keep it on the whiteboard while we're working it. Snapshot, sorry. Let me just get a screenshot. So it's this problem right here. So we define a set, which is the real numbers with the exception of -1. And then we want to show that the binary operation that the author is describing here actually describes an operation which, together with that set of elements, forms a group. So there's a lot for us to verify in order to pull that off. So that's why I don't want to check every single one of these properties. But I do want to check a couple just because it's really a neat sort of scenario in which we can do some algebra. So let's get started on this. This is one of the problems that I had assigned for homework, so this is a good one for us to be talking through today. So let me get the copy of that up on our whiteboard so we can refer to it as we're going. Here it is. Okay. So we're letting S be the set of all real numbers with the exception of -1. We're defining a binary operation in this way. A star B is equal to A plus B plus A times B. And these pluses and times are the addition and multiplication operations on the real numbers. And that's an important observation because when we go to actually verify some of these properties, we're going to need to know something about the properties of the real numbers and their arithmetic. Those are things that in our class we're going to take for granted. Things like the associativity of the multiplication in real numbers. Those we're going to take for granted this semester. But really, those are things that as math majors we should also win. We should prove them at some point in your mathematical development, probably in your course on real analysis. So that's the plan. We want to show actually not only that this set together with this operation forms a group, but also that it forms an abelian group. So this is good because it also gives us a little bit of a hook into what we're doing in the next section as well. So, as always, this problem is asking us to prove something. And because it's asking us to prove something, I don't want to just open up my word processor and immediately start trying to write a proof. That's kind of a recipe for disaster. So instead what I want to do is just pull out a piece of scrap paper. And this week, I actually brought a napkin with me. So here's a napkin. I'm going to do the work on the back of it. Picked it up at the Hilbert Hotel bar. Great hotel. They always have vacancies. And let's do some of our scratch work here on the back of this napkin. And then afterwards, we'll worry about actually trying to write up a proof around this idea. By the way, for the interest of openness, this problem, this exercise, is taken out of Thomas Judson's Open Educational Resource online algebra text. It's from his It's from his chapter that's entitled Groups. So again, if I'm trying to prove that this set together with this operation is an abelian group, then that means that I really need to, in principle, show a total of 5 things. Sorry, I'm counting incorrectly already. I really need to show 5 things. And again, I don't want to do all 5 of these in this video, but I would need to show that this operation is associative. I would need to show that the closure property is satisfied. I need to show that the my stream is kind of having some issues, so let me real quickly just go verify what's going on. Sorry about that, for those of you watching. Let's see here. Yeah, that's the hard part about doing this on a smaller screen here. Let me take the chat window, make it a little smaller, and buy us a little bit of space. What else might be? Oh, I think I see what's happening. Let's do that and try again. If you're watching on the stream, is this looking better than it was before? If it's not, again, please let me know. I'm going to keep talking on the off chance that that it is working, and we can just keep going. So associativity we have to show. Closure we have to show. Great, it's working. We have to show the identity property holds. We have to show that the inverses property holds. And then, because of the word abelian sitting right here, that means that we also have one additional thing to show, something that we wouldn't have to show, and in fact we wouldn't expect to generally be true unless our group were an abelian group. So this one's kind of a special one. I'm going to set it in a different color here. For abelian, we would also have to show that the commutativity property holds. After all, that's what abelian means. Abelian means that the operation in this group is commutative, that if I operate on 2 elements and I operate in the opposite order, that I get the same result either way, which is not true in groups in general, but in this example, we're asked to show that it is true for this particular structure. So I don't want to go through all of these properties because we don't have the time in our stream today. But I thought it would be interesting for us to take a look at least the property of identity, which is kind of an interesting one, and also the property of closure. To me, working through this problem, these are the two in which there's the most subtlety. They give us the most interesting things to try and set up and prove, because they're going to require us, again, to think deeply about what these properties actually mean in the general setting of a group. So let's make some room on my hotel napkin here. And let's get started with the closure property. So first thing I want to do here is remind myself what the closure property actually says. Closure property says that for all elements in my set, let's call them G and H, in my set of elements, if I apply my binary operation to those elements, that I should get another element in my set. We have G star H needs to belong to S. So this is our burden of proof. I'm going to kind of put it in a box up here because this is the thing that we want to show is actually true. Maybe I'll highlight it instead of putting it in a box. So that's the thing I want to show is true. So how do we start moving in that direction? Well, I would recommend starting by reminding ourselves of what the set S actually is. What are the elements in this set? They're real numbers, except, so this is the little set theoretic subtraction, we're taking away the number -1. And that's super important, because if it weren't for that, this would be a super simple thing to verify, because the real numbers satisfy the closure property under addition and under multiplication in general. So it's always true that the sum of 2 real numbers is real, and that the product of 2 real numbers is real. And so if it weren't for this taking away of -1, this would be very quick. If A and B are both real, then A plus B plus AB are also both real. And so on my napkin, I'm just going to kind of write down, again, this is my scratch work, so I don't have to be super formal. Obviously, G plus H plus GH is real when G and H are real. So that's not going to be the interesting part. The interesting part is that we have to show not only that they're real, but they belong to S, this particular subset of the real numbers. And this subset is characterized by the fact that it does not include a single real number. It includes every real number but -1. So really the hard bit is what we're really trying to show here is if G and H belong to S, then let me translate that. G and H belonging to S means that G is not equal to -1 and that H is not equal to -1. So those are the things that we're assuming in this first step of closure, right? That the universe is going to pick for me a G and an H in my set, and all I know about that G and H is that they belong to S. Therefore, they are real numbers, but are not equal to -1. And then what we have to deduce is that G star H belongs to S as an implication of this. So we have to show that that first piece, G is not -1 and H is not -1, needs to imply that G star H, which by definition is the sum of G and H added to the product of G and H, we need to show that that's not equal to -1. So this is really the form of the implication that we have to prove here in order to establish closure for this particular operation. So this is kind of it's a brain teaser at first, right? It's saying if you give me two real numbers and all I know about them is that neither one of them is equal to -1, then how do I know that when I do this combination of arithmetic to them, that the result is also not equal to -1? Why should we expect that to be true? Well, we shouldn't expect it to be true. We should verify that it's true. In the form that it's written, makes me sort of think that it's probably not going to be the best idea to use a direct proof. Right? If I try to use a direct proof, then I'm going to start by assuming that G and H are not equal to -1. And if I assume that something is not equal to -1, it's harder to use that thing as part of a later algebraic argument, right? It's much easier, it gives us a lot more to work with, if we can assume that something is equal to a specific real number, rather than not equal to a specific real number, for the sake of our argument. So rather than trying to approach this in the form that it's written, I think I would rather approach this in its contrapositive, which is logically equivalent. So if I prove one of these, I have proven the other, because they both have the same truth value. So what is the contrapositive of this statement that's written down right here? Well, the contrapositive always begins with the negation of the conclusion first. So I'll write down here the negation of this statement. G star H is not equal to -1. And that negation would be, of course, the thing that happens exactly when this does not happen. And when that doesn't happen, this does. Right? So the sum plus the product has to equal 1 in the contrapositive, and we have to show that that implies. Now I need the negation of my premise, my antecedent up here. And here the hypothesis was that G was not equal to -1 and that H was not equal to -1. When I negate this statement, both of these inequalities will become equalities. G equals -1, H equals -1. But also, the conjunctive connective that I have up here, in other words, the word and, let's not be too fancy about it. The word and, in logic, when we negate an and, it turns into an or. I was actually just talking with my Math 105 students, my Math for Non-Majors students the other day, about this idea. We just started our unit on logic also, that if my burden of proof in a courtroom is to show that this purple statement here is false, right? If somebody is claiming that both G and H are not equal to -1 and I'm trying to prove them wrong, then my burden of proof is I either can show that G in fact is -1 or that H is in fact -1. Either one of those two will falsify the statement we have written here. And what's great about the contrapositive now is that we're using positive language to characterize G and H. G is equal to -1 or H is equal to -1 is now our burden of proof. And our assumption, if we're going to prove this statement directly, is G star H is equal to that should say -1. I'm sorry, that's a typo. -1. Okay? So that feels like something that we can approach with a direct proof, but I've run out of room on my napkin, so I need a second napkin here. Let me go and grab one. Okay, let's drop this. So I'm just going to slide this around a little bit here. All right, let me drop this second napkin down here on top of the first. There we go, second napkin. So let's continue our proof on this second napkin. So again, on my scratch work, I'm going to say, let's suppose G plus H plus GH is equal to -1. And what I'd like to do is somehow understand from this equation something about G and H. Well, the left-hand side of this equation here is a polynomial. In fact, it's a quadratic polynomial, degree 2 in G and H, because we're multiplying the G and H together, so the total degree is 2. So if I'm going to try and learn anything from this equation, what I might try and do is use any strategies that I know for solving quadratic equations. And as with any polynomials, the best idea is to try and get all the terms to one side. So I'll take this -1 and I'll add 1 to both sides so that the other side of the equation is equal to 0. 0, of course, is the magic number for doing anything with polynomials, because now we're going to have the option of factoring what's on the left-hand side. If I can factor what's on the left-hand side, then the zero factor property, which is another one of those properties of real numbers that we're going to take for granted. But bear in mind, we cannot take for granted in general in more abstract settings, but we'll be okay with it for now. The zero factor property will let me factor and then split apart my equation into simpler factors. So the question then becomes, how in the world do I factor GH plus G plus H plus 1? Well, in case you haven't seen this factoring technique before, let me share it with you. This is something that I learned in the process of teaching the remedial algebra course here at Bridgewater. Because I found this was probably one of the best ways to help new algebra students come to grips with this technique that we're about to use. So what we're about to do is factoring by grouping, which is something that even math majors don't have to do that often. But when it's helpful, it's super helpful. And the way that I like to do it, just to keep straight exactly what's happening in my head, is I like to take all 4 of these terms and put them all into a grid here, a little 2x2 grid. So I'm going to put GH up here, I'll put G over there, I'll put H here, and I'll put 1 over here. Okay. So I've got each of my 4 terms inside one of these squares. And what I want to do is try and factor. And what I mean by that is I want to try and write something outside of here and outside of here. So actually I'm kind of making a little Cayley table, if you like. It's a little multiplication table where I've started by filling in everything inside the table. My question is, what were my elements on the outside of the table? It's not really a multiplication table because I probably don't have the same thing up here on the first row as I have here on the first column. But the idea, again, is that whatever is here has to be the product of this thing and that thing, and so forth. Okay. So the way I like to start doing this is by picking out any row or any column. Let's say I pick this first row here. And I ask myself, what can I factor out of this first row? What do those 2 terms have in common, GH and G? Well, it doesn't take too much self-reflection to observe that G is in fact a common factor of both of those 2 things. And now that I've written a G out here, I know what's going to go in these 2 spaces. Right? The missing factor between G and G times H is going to be H. And the missing factor between G and G is 1. G times 1 is equal to G. Right? So now I have 3 out of the 4 entries outside of my table filled in. Now all I have to do is figure out this last one. And so I ask, what is the missing factor between H and H? And that missing factor is 1. And finally verify that the 1 here and the 1 here multiply together to give me this 1 right there. So we've successfully factored using this little grid method. We factored the expression on the left side of my equation into a product of G plus 1 times H plus 1. And if you don't believe me, FOIL it back out. You should never believe me on faith, of course. But multiply it back out and you'll find out that this is indeed how it factors. You may choose to factor by grouping using the old traditional method, just looking in the expression and saying, well, I can factor a g out of these two and then kind of cross my fingers and hope for the best and then factor out an h plus 1. But I really like this grid. It really helped me when I was teaching remedial algebra to come up with a way of really organizing your thought process in factoring by grouping a little bit better. But hopefully now you can see why that factoring step was so crucial, because now that I have this product on the left side of real numbers, and the right-hand side is 0, the zero factor property of real numbers, which, again, we're going to take for granted, but we shouldn't take it for granted in more abstract concepts, lets me split this apart and say that the only way that their product was 0 is if one or the other of them was already equal to 0. So there's a little or implicit in between these two things. Sorry for writing a little bit small. But when we solve each one of these equations, we get g equals -1, h equals -1, and again, there's that implicit or in between. And sure enough, that was exactly the thing that I was supposed to try and conclude here in my contrapositive. So all of my napkin work appears to be done for this problem. Now we just have to actually write up a proof that would communicate in writing the process that we just sort of talked through together. So if somebody wasn't watching the live stream today, and there's at least 7 billion people in the world not watching today's live stream, then they'll know what it was that we just did. So let me start by just writing proof of the closure property. Because I'm not doing the whole proof of this thing, I want to be explicit about what exactly it is that I am proving. So job 1 in any proof write-up, as always, is to signal to the reader what is the overall strategy, what is going to be the form of our argument, and if we are making an appeal to any sort of theorem or other result from outside, what is that other result? Well, we're not having to make any appeals to outside authorities. All we need to do first is make an appeal to the definition of closure, the way that I did here at the top of my napkin. So, all right here, we wish to show that for all g and h in my set S, that g star h is in the set S. So remind the reader of the definition that we're invoking here. So that tells them what we're wishing to show. Now, looking again over at my napkin, I remind myself that the meat of my argument was actually turning this into a contrapositive. So here's a good place for us to tell the reader that that's what they should expect. So here I'm going to just use one of my bylines, by contraposition, which is a really fancy byline to say that we're about to write a proof by contrapositive. This is maybe a little bit overly formal. So we can say something else that shows that you've got something up your sleeve. So maybe, suppose in fact, that G star H does not belong to S. Okay. And then, again, tipping your hand to the contrapositive argument, we'll show that either G does not belong to S or H does not belong to S. Right? So again, the form of what I've written so far is that we say what we're about to prove, we unpack the definition so that the reader knows what exactly our burden of proof is going to be, and then I've written the statement in red which indicates that we're going to make an indirect argument. We're going to prove by contraposition. Suppose that G star H is not an element of S. We'll show that either G is an element of S or H is an element of S. But I want to pause here because I've done something unforgivable in my proof. The unforgivable thing that I've done is that I've supposed something about a pair of elements, G and H, which don't yet exist in my proof. They don't yet exist. I haven't brought G and H into existence yet. They're not on my workbench as an architect of this proof. And I know that because if I look up, right, there needs to be an explicit place above here where I have brought those elements into being. A definition doesn't do that. A definition just says that any G and H that the universe brings into being, we need to show they satisfy this. But the universe has not had an opportunity to bring G and H into being yet. And I'm speaking here as though they have. So what I need to do, this is much easier on a whiteboard than it is on a pencil and paper, because you'd have to erase a lot of stuff. But what I really need to do is I just need to scoot this down and leave space to add a line right here, where now the universe is going to bring a G and an H into existence. And I have to let the universe do it because we're making a universal claim, right, for all G and H that are elements of my set. So here we have to give the universe the first move in our little game. Let G and H belong to S. And if we really want to be overbearing about it, and remind the reader that it's not me as a proofwriter that's choosing it, but rather it's the universe choosing a G and an H, and so we have to deal with whatever G and H might be chosen. I'll say, let's let G and H be arbitrarily chosen. And by the way, what that does is it also kind of turns our contrapositive argument into a contradiction argument, because now what we say we're about to show is that either G is not an S or H is not an S, and that contradicts the assumption we're making here when the universe brings G and H into being. For me, that's not a super important point to get that distinction between contradiction and contrapositive, but other logicians may feel differently. Okay, so now we've set up the scaffold of our proof. Right, universe picks a G and an H, and we're going to say, let's suppose that G star H does not belong to S. We're going to show that this assumption cannot be sustained, that either G is not an element of S or H is not an element of S. And so then we're going to prove this red statement using a direct argument. We're proving the contrapositive using a direct argument. So that means we're going to assume that G star H is an element of S, is not an element of S, I'm sorry. So assuming the G star H doesn't belong to S, now we can say, we can make this little obvious observation from over here. G star H is definitely going to be a real number, so we don't have to worry about not belonging to S because somehow it's no longer real. Assuming G star H is not an element of S, since clearly, and be very careful using words like clearly in a proof, unless something really is just glaringly obvious. I'm going to just use it here mainly to economize on space. Since clearly G star H is a real number, is in the set of real numbers, and again, that's by the closure property of real numbers, but since we've ruled out the possibility that G star H is not real, assuming that it's not an element of S, this means that G star H must equal -1, right? Because my set consists of all reals except for -1. If this thing doesn't belong to my set and yet is a real number, that must mean that it's exactly equal to the one element which we took away from the set S, one real number which we are not permitting. This means G star H is equal to -1. Okay, so now we know G star H is equal to -1. Now I can go directly to this napkin over here. Right? This means G star H is equal to -1. So G plus H plus GH is equal to -1. And here's a good opportunity to use another byline, because if it's not clear why I'm getting that next line of my proof, I can remind the reader where this sudden algebraic expression is coming from. It's obvious to me right now writing this proof, but to somebody picking up this proof on Mars 1,000 years from now, they might not be in our headspace. So I hope they're not in our headspace if they're a Martian. So let me make a little bit of space here for a byline. By the definition of star. Right? So by the definition of the star operation. And what that does, again, for the reader, is it forces them to look back up here and say, oh yeah, G star H is defined to be the sum of G and H added to the product of G and H. Right? So now we know where that equation is coming from. And then the magic happens, right? Now we go back to our napkin over here. We add 1 to both sides. GH plus G plus H plus 1 is equal to 0. By the way, notice I'm also implicitly using the commutative property of addition of real numbers here because I traded places with the GH and the G plus H. I'm not going to make a note of that, but I suppose we could. Because we would also have to note the cancellation property, which permits us to add 1 to both sides and still have an equation with the same truth value. But because those are all things that for the real numbers we're just going to take for granted, I'm not going to cite them here. Then we do our factoring. You know, and in a proof that I'm submitting to an academic journal, I'm not going to probably show them this step. I'm just going to factor. And if the reader remembers how to factor by grouping, then they get it. If they don't, then, you know, maybe they should go teach an intermediate algebra class in college, and they'll learn it like I did. And then we can split apart this equation into 2, again, using the zero factor property of the real numbers. Actually, this time I probably do want to cite that. Not really for the sake of any reader, but for the sake of you, an abstract algebra student who's looking at this proof, just to call attention to the specialness of that fact, by the zero factor property, also called sometimes the zero product property. And that's a property that the real numbers have. Okay. But it's not a property that we can take for granted in just any algebraic system. And then again, using the cancellation property of the real numbers, subtracting 1 from both sides gives me G is equal to -1 or H is equal to -1. And that's exactly what we wanted to show, because after all, try and get this spaced apart here. That's exactly what we wanted to show, because as soon as G is equal to -1 and H is equal to -1, since G and H are real numbers by assumption, right, because G and H belong to S, we know that they must be real in particular. This must mean that by definition of S, this means G doesn't belong to S, or that H doesn't belong to S. And I'll put the byline in there also. By the definition of my set S, G is not equal to S, or H is not equal to S. And at this point, I'm going to declare victory. Right? And I can declare victory, again, looking back up at the earlier part of my proof, where I told the reader, first of all, I want to show that the closure property holds, and this is what closure means. But then, so I let the universe choose a G and an H for me to satisfy this universal quantifier here at the front for all G and H. So universe picks a G and an H. But then I tell the reader, I'm going to prove this thing indirectly. I'm going to prove it by contrapositive. And so what I say here is we're going to suppose that G star H is not an element of S. We will show that either G doesn't belong to S or H doesn't belong to S. And now that we've shown that that logically follows from this, then we've completed the argument. So this, again, I think is sort of typical, first of all, of the process of working with the definitions of a group and deploying them in your reasoning. And reminding yourself that the operations that we define in abstract algebra are not always familiar operations. In this case, the operation star was built upon operations of arithmetic on the real numbers that we already know and love, and we actually had to use properties that arithmetic of real numbers enjoy in order to complete our argument. Right? But really, I think the trickiest part of these is just keeping your focus on the operation that's at hand, even when it's built out of other things like addition and multiplication and stuff like that. Just reminding yourself that the operation in this purported group is always going to be this star. Anytime we combine two elements of S, we're going to combine them together using that operation. And so this is probably, I think, the most subtle one of the 5 things that you have to verify in this problem to show that this S is an abelian group. Probably the runner-up is the identity property, but now having seen this argument, hopefully if you sit down and try and make the argument about the identity property for this group, you'll see pretty quickly how to do it. It's a little bit simpler than the one that we just did. So I want to pause here and ask if there are questions or clarifications that people would like on this proof before we take another step forward, and I want to do some talking about Cayley tables for today's stream before we wrap up. Those of you that have me in class know that I don't tend to spend long periods of time lecturing. That's actually a muscle over the years that has kind of atrophied for me. So I'm finding that anytime I talk for 30 or 40 minutes straight, such as on a live stream, I get a dry mouth, a sore throat, that kind of stuff now. I'm just out of practice, but in a way, I'm kind of okay with that. Let's move forward and do a little bit of Cayley table. Well, let's think about Cayley tables. So what I'd like to do is build on something we did in our last live stream last week, which is last week we used the idea of a Cayley table to ask the question, if somebody hands me 3 elements and says make a group out of these 3 elements, can I do it, first of all? And second of all, if I can do it, what kinds of choices do I have to make along the way? So is there more than one way to do that? And so what we found last time is that there was, in fact, a way to make a group out of a set of 3 elements. Not only that, there was only one way in which it can be done. There's only one way to make a group out of those 3 elements. And so what an algebraist would say is that there is a unique group of order 3. Right? Order 3 meaning there's 3 elements. Unique means that there's only one Cayley table that I can write down that will satisfy all of the properties of being a group. And so let me write it down again, just to remind us of what it was. So if I call my operation this little circle operation, every once in a while I like to switch that up instead of just making everything a dot or just using juxtaposition. So we'll make circle the operation in my group. My elements are A, B, and C. A, B, and C. And the only way in which to make a Cayley table with these elements that satisfies the properties of a group was to, first of all, single out one of them to be the identity element. If I single out A to be my identity element, then that means that anything that A combines with is going to be equal to itself. So when I combine it with A, it becomes A. With B, it becomes B. With C, the product is C. And the same is true going the other way, because identities and groups are two-sided by our assumption. Okay. So there's my identity element, which again we recognize by the duplication of the first column in its column, as well as the duplication of the first row in its row. Right. So I have an identity element. And then once we figured out how to fill in this square right here, we figured out it couldn't be A, because if it were A, then this would have to be C, and if B times C were C, then B would have to have been an identity. But B is not the identity, because the identity element in any group is unique, so we can't put a B here. That was a very quick recap of what took us about 10 minutes to realize in the last live stream. So we figured out that this has to be a C. And if that's a C, then since B has to have an inverse, and so far nothing else on this row is combining with B to give me the identity, namely A, that means that A has got to go there. And then likewise, since C has to have an inverse, we need an A, since this B has to have an inverse, we need to have an A in its column as well, and so this entry has to be A. And finally, if I put a C here, then C times C is equal to C, which makes C like an identity. That's not good. If I put an A here, C times C is equal to A. That makes C its own inverse. But then since C times A is also equal to C, cancellation would imply A is equal to C. So the only way to fill in this entry was with a B. So this is the only Cayley table that we can make that meets the criteria to be a group with 3 elements. I want to make one quick point before we go further, and that is, it's related to something we've been talking about in class. This is what we're claiming here, the only way to make a Cayley table out of this set of elements. But we did have to make a choice. We had to make at least one choice. Right? we had to choose which of these three elements our identity was. And so that's a choice that we want to kind of agree doesn't matter. So it doesn't matter if A, B, or C is chosen as the identity. Right? So I would have still the very same algebraic structure if I had done, let's say B is my identity. Let me write it here in the middle. So if B was my identity, then B multiplied by anything is going to equal itself, and so BA is going to equal A, BB is going to equal B, BC is going to equal C. Same thing here on this row. So if B were my identity, I would have to fill in these squares in that way. But then AA would have to be C, AC would have to be B, AC would have to be B. Wait, that's not right. Oh no, that's right. CC has to equal A. Right, so I would end up getting this Cayley table. And you might say, well, this looks like a different Cayley table to me, right? Because if I just sort of read the entries in this table, ABC, BCA, CAB, what I have here is actually a permutation of the rows, or equivalently a permutation of the columns, right? What I've kind of done is I've taken this row and I've moved it up here to the top. I've taken this row and I moved it down here to the middle. And then I've taken the ABC row, the BCA row rather, and bumped it down. But is that really a different algebraic structure? And my claim is that it's not, right? That using the language we were talking about in our last class yesterday, let's suppose that let me give these elements over here slightly different names. Let me call them A prime, B prime, C prime, just so that we can clearly distinguish between them. Right? That if I compare these two things, the A, B, and C from the first table that we wrote down, and the A prime, B prime, C prime from the table that I just wrote down now, that there is a, I hope, clear comparison between how they work. That A, which is the identity in my first group, correlates to B prime, which is the identity in my second group. And then since this row, the row BCA from this table ended up getting bumped down to the third row, my C prime row, that kind of indicates that what happened was that B, the old B, is the new C prime. And then the CAB row from over here became C prime, A prime, B prime, so the old C is the new A prime. Right. So what I have here is I have a function. Again, let's call this function by the Greek letter phi, or phi, if you like. I have a function which is one-to-one and onto that relates the elements in my group on the left with the elements in the group on the right. Not only is it a bijection, it also does some other nice things. Namely, the identity element of the first group and the identity element of the second group are related one to another by this function. So that's something that not every bijection between two sets of three elements, in this case, is going to do that. And so it gives me a little bit of reassurance that this function is not only relating elements together, it's relating similar elements together. The elements that are acting abstractly in the same way in these Cayley tables are being related together. At least the identities are. And then we can verify again that B and C are acting in similar ways in this table as A prime and C prime were in this table. So all of this is a roundabout way to say that choosing a different identity, all it really does, the only thing it really accomplishes, is it just accomplishes a renaming of the elements. So another way to say this is that what we want not to matter is if we call the elements by different names. If we rename the elements. If we rename the elements, then the Cayley table that we get, we want to be able to say is the same. It's still the same. Whatever we write down shouldn't matter on the ways in which we rename the elements, or another way to say it, the way in which we order the elements of my set, right? Because a set doesn't care about the order of its elements. We could trade this around to BAC instead, and then my Cayley table's rows and columns would be permuted, but all the rest of the structure would still be the same. And again, I want to keep this word the same here in scare quotes. until we really have a firm foundation on what that means. This also tells me, for example, that if I were to write down a different group of three elements, a group that looks different, let's say addition of residue classes of integers mod 3, 0, 1, and 2. Right? That's a group that we know has three elements. Right? There are three equivalence classes for addition modulo 3. And when I apply addition to these, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, and so on this way, and so on this way. Apologies for all the brackets. 1 plus 1 is 2, 1 plus 2 is 0. Terrify your roommates who aren't math majors by telling them 1 plus 1 is now 0. But so we come up with this Cayley table. And when I look at this Cayley table for addition mod 3, so this is the Cayley table for Z3, right? This looks exactly the same in structure to this abstract group that we just wrote up here, right? With the role of A, the identity, being played by the equivalence class of 0, the role of B played by the equivalence class of 1, and the role of C played by the equivalence class of 2. And so if we agree that the names of elements don't matter, and only their relationships in a Cayley table matter, then this group, Z mod 3, is the same as this abstract group up here. Maybe we should call it G. If I call this group up here G, then we will say G and Z3 are the same. And what we could do is we could set up a function, phi, from G to Z3. And this function would have the property that if I apply it to A, I'm going to get the element which behaves like A in my Z mod 3 group. If I apply it to B, I'll get the element which seems to behave like B. And if I apply it to C, I'll get the element that behaves like C. Right? So if I define that function, it's one-to-one and it's onto, so it's a bijection on the set of elements, but also it seems to be relating together elements of these two groups that act exactly the same as one another within the structure of the group that they inhabit. We've also seen other groups that would satisfy this structure. Let's suppose we think about the group of symmetries of a triangle, but let's pin that triangle down on the table so that it can't actually move. We can't pick it up and flip it over, is what I'm saying. If we can't pick up and flip over a triangle, then all that we can do is rotate it. I'm going to take this opportunity real quickly here to pull up our dihedral group explorer, just because I can't keep from showing this app off every time I get a chance. Let me load up my Scratch account here. I think because I'm streaming video from my home internet, this is being a little bit slow, but once we get it loaded in here, we'll be okay. Here we go. So here's my Dihedral Group Explorer Scratch app. Again, you can find a copy of this on my website, mathematics.com/abstract, to play around with if you like. Let me see if I can move this into the center of the screen a little bit more easily. Well, how about I share the screen a little bit like this? There we go. So if I pin my triangle down to the table, it means I can't pick it up and reflect it, right? All I can do is rotate it. And so I'll have an identity, which is the symmetry that I get by not doing anything to this triangle. I'll have a rotation, a single R, right? And then the other thing that I'll have is the rotation going the other way, which is the same as the inverse of the first rotation, right? Because for a triangle, rotating 120 degrees counterclockwise, rotating 120 degrees clockwise is the same as 240 degrees counterclockwise. So, and each of those is a symmetry of the equilateral triangle. So in D3, the dihedral group of the equilateral triangle, suppose that I just consider this set of elements, just the identity, which means we do nothing to this, just the single rotation, which looks like that, and just the twice iterated rotation, which ends up being a symmetry that looks like that. Those three are all distinct elements in the dihedral group, and we know how they interact. We know that the E, for example, is our identity, and so if I compose it with any other symmetry, I'm just going to get that same symmetry back. We also should know that R composed with R is going to give me R squared. but that r composed with r squared gives me r followed by r, which gives me indeed the identity back again. So put an identity there. And then finally, r composed with r is going to give me, whoops, sorry, this is a typo. This is an r squared. R squared composed with r, same story. R squared followed by another r. That gives me the identity. And r squared followed by r squared gives me a total of 1, 2, 3, 4 rotations. That's the same as only having done one rotation, so that's r. So what we've got, if we take a look at the Cayley table that we just made with these three symmetries, we would call these the orientation-preserving symmetries of the equilateral triangle. Notice we can always read the numbers 1, 2, and 3 on the vertices. They never get reversed in the action of these elements. And sure enough, this also follows the same pattern that we saw here, which is the same pattern that we saw here, right? That this, what we would say, is a subgroup of D3, because notice we're using the same operation as exists in the dihedral group, but we have the closure property that we never get a TR or a TR squared or something else here, that this Cayley table satisfies the closure property, but we're only listing a subset of the elements of D3. So we're going to call this subset a subgroup of D3. And actually subgroups are a big deal. They're the next thing that we're really going to dig into. So this right here is a subgroup of D3. But again, this group, this Cayley table over here, is the same as this Cayley table here, which is the same as that Cayley table over there. And so what we can say is, let's set up a function. Call this one psi from D3 to Z3. So the two Cayley tables on the bottom of my screen here, that if I take and I relate the identity element of D3 to the 0 equivalence class in Z3, and if I relate R to the element 1, and if I relate R squared to the element 2, then this is a function that not only is a bijection, so it's one-to-one and onto between these two sets of elements, but also it's relating together similar elements, right? The identity here gets related to the identity there. The element which behaves like R behaves like 1 over on this side, and the element which is related to the R squared behaves in the same way that R squared does, right? These two Cayley tables are exactly the same. The only difference is that we've renamed the elements, right? And so I think we can agree that these two groups are also the same. And by the way, I shouldn't say D3 here, because that would be the entire dihedral group of the triangle. So my apologies. Let me put in here H. And I'm going to call H this subset of 3 elements. H equals this set of elements, right? So that means that this group, H, is the same as the group Z3. The only difference is in what we're naming the elements. One last sort of parting shot on this example, which also, again, is going to kind of help us to remember how to use Cayley tables. Suppose for the moment that I'm wondering whether or not, and this is a definition from our next chapter, but I think it's still valuable to think about now. If I'm wondering whether or not this group here is a cyclic group. So we know is G a cyclic group? We know it's a group. We know it's the only, up to our notion of sameness, it's the only group that we can make out of 3 elements. We can also directly verify that it's abelian. BA is equal to AB. CA is equal to AC. This Cayley table is symmetric across its diagonal, right? B here, B here, C here, C here, A here, A here. So it's abelian, but what we can't immediately tell is whether or not it's cyclic. Remember, cyclic means that the powers of only one element are enough to account for all the elements in that group. So let's try to show that, let me pick on an element. Let's show that C is a generator. If I show that C is a generator, it would mean that the set of all powers of C generates the entire group G, and therefore G is cyclic. So let me endeavor using this Cayley table to show that C is a generator. So to do that, I just need to start writing down some powers. What's the first power of C? What's the second power of C? What's the third power of C? If we need to, what's the fourth power of C? What's the fifth power of C? And so on. And let's use the Cayley table to figure these powers out. Well, the first power of C is, by agreement, always just equal to itself, right? The first power of any element, by convention, is itself. What's the second power of C? It's C times C, and so I'll look it up here. It's going to be B. Let me just put a little label next to that B to write that that's C squared, right? So C squared is equal to B. If I want to find out what C to the third power is, then what I want to do is take the second power and multiply it by another copy of C. So in my Cayley table, what that looks like is I'm just going to take this B from over here and scoot back over into the first column, make this a B, and then multiply by another C. Right? So B times C is going to give me A, and that A, therefore, is C to the third power. And remembering that A was also the identity element in my group, now pretty much that means that I can stop. Because if I were to keep going, if I were to try to compute the fourth power, that means I would take this element and put it back into my first column, then multiply by C one more time, and I would end up out here. And that tells me that C to the fourth power is equal to C. But we've already accounted for C in my powers of C, and so we really didn't need to keep going, right? That the first, second, and third powers of the element C account for all three of the elements in my group A, B, and C, and therefore the answer to this is yes. G is in fact a cyclic group. The way to show that a group is cyclic, if you can, is to explicitly come up with a generator. Here's an element of this group, C. I'm going to prove to you that C generates the entire group. The powers of C give us absolutely everything. So that actually tells us one more thing than we came in with, right? We know that if I have three elements, then every way in which I can make a Cayley table with those three elements that satisfies the criteria of a group, there's only one way to do that, up to the renaming and the relabeling of the elements in that group. So that's the first thing we learned. We also already knew from our last live stream that that group was abelian, because the only Cayley table we could make was symmetric, right, across the diagonal. But now we also learned something else. Not only was it abelian, the group is actually cyclic. And furthermore, these other groups that I have on the screen right here, those groups are all the same as this group of order 3 that we made abstractly, just using a Cayley table argument. Which would mean, therefore, that these other groups are cyclic as well. Since if C is a generator of this group, then anything that we correlated C to by that idea of sameness in these other groups can also be a generator for these groups. So 2, the equivalence class of 2, mod 3, is a generator for the additive group of integers, mod 3. R squared, the 240-degree counterclockwise rotation of an equilateral triangle, is also a generator for this subgroup of the symmetries of an equilateral triangle that consists of just the orientation-preserving symmetries. So that's the power of abstract algebra, is that if we understand well enough the properties of the abstract structure, C is a generator for this group of order 3, then that means that any place in which we see that abstract structure showing up elsewhere in more concrete forms like this one or this one, that abstract property is still going to hold in those more concrete settings. In the Common Core state standards of mathematical practice, one of the things that now permeates the K through 12 math curriculum, so future teachers listen up, one of the things that permeates the standards of mathematical practice is the notion that a student of mathematics should be able to look for and make use of repeated patterns and structures, right? So if I see something happen in one context over here, then I should be able to look for an analogous pattern in a new context somewhere else and be able to then make use of what I observed the first time around. Abstract algebra, really one of the biggest reasons that our future teachers take abstract algebra is to gain that practice. I mean, that really is what this subject is about putting our fingers on those patterns that we can identify in an abstract context, so up in the Platonic sphere of form, the perfect forms of these things. If we understand what those patterns are in the abstract, then when we see them showing up in the concrete, we'll know exactly how they work with one another. And it becomes independent of the context, and it becomes about the form of the abstract. So I hope that this was helpful today. We had a chance, again, to talk first about how to prove, using the properties of a group, that a group satisfies closure, identity inverses, associativity, abelian, right? We have to show commutativity in that case. We just walked through an example that used the closure property. This was taken from Judson's abstract algebra text from the groups section. It was one of your homework problems. And second of all, we talked a little bit more about how to use Cayley tables to continue to refine our idea of what sameness is in a group. And also, we gained some practice using Cayley tables to compute the powers of an element, right? Just by repeatedly multiplying by c. It just means, find the next element in the c column after we take the element that we started at and gone back to the beginning, right? So c to the first power is here, c to the second power is there, c to the third power is there, c to the fourth power is there. Then c to the fifth power would be back down here, and so forth, right? So the greatest thing about a Cayley table is that it tells you everything about the group. It means that you never have to do any concrete calculations in that group anymore, because the Cayley table has all the products already inside. And so this is really, really great. When you have a Cayley table, it's amazing. Of course, the big question of abstract algebra is, how do we understand groups well enough when we don't have a Cayley table in front of us? Or if we don't even know what the Cayley table might be, what can we still say about groups in more generality? So as we're wrapping up this part of the course, Cayley tables are going to slowly start to fade away this semester as we begin to get more and more sophisticated about using the definitions, properties, and theorems that we can prove are true for any group, regardless of what its Cayley table might look like. So I hope this was helpful. I will see those of you that are in my class tomorrow. We're going to start the hour with a quiz, and then we're going to continue the conversation we had last time about thinking about the orders of groups and the orders of elements within those groups. So we'll see what kind of conjectures and what hay we can make there when we come back to class tomorrow. So I will see you all then.